Right, now we're going to talk about the presence of ions in solutions. So strictly, ions are not molecules, so they don't have necessarily intermolecular forces. So our intermolecular forces strictly are the dispersion, the dipole-dipole, and the hydrogen bonding. However, ions are common in solutions, so we need to talk about how ions influence intermolecular interactions, okay? So ions are permanently charged. Permanently. Okay, we almost might call them purely charged. Okay, when we have a polar molecule, that molecule is sharing some of the positive and some of the negative. With ions, we have no dichotomy there. We have either only positive or only negative. So they're extremely strong in that charge. So when we have an ion in solution, let's say some sodium plus, that ion is going to influence anything around it that it can. Anything with a negative charge is going to be attracted to it. So if I have a water molecule nearby, right, and a water molecule is a polar molecule, so it's going to have a negative and a positive end. So my sodium is going to be attracted to the negative end of the water molecule. Right, so we have an ion and we have a dipole. Right, so this is called the ion-dipole interaction. Right, and it's stronger than hydrogen bonding. Okay, when we have a permanently polar molecule attracted to a permanently charged ion, the ion-dipole interaction is going to be stronger than hydrogen bonding. And we can have it with negatively charged ions too. If I have a water molecule with its negative and positive sides. If I have a chlorine nearby, the chlorine's negative charge is attracted to the positive end of the water molecule. Okay, and this is in fact how sodium chloride comes apart in solution. When we put it in water, these ion-dipole interactions are very strong. So the water molecules actually pull the sodium chloride apart when it gets into water. Now, ions can also interact with electron clouds. Okay, so if I have a sodium ion, for example, I'm going to keep using sodium because it's easy. And if I have an electron cloud full of negative charges, right, let's call this a nonpolar molecule. Right, so it doesn't have a particular end that is positive or negative. But electron clouds are polarizable. Okay, so what's going to happen is my sodium is going to be attracted to the electrons, and it will actually pull the electrons all over to one side and polarize the cloud. Okay, and this is what's called an induced dipole. Right, so we have an ion and we have an induced dipole, so we would call this the ion-induced dipole interaction. Right, so this one is actually slightly above dispersion, right? This is a fairly weak interaction because it's essentially still a dispersion interaction, but we're causing it by the presence of an ion. Now the same thing can happen using a polar molecule. All right, so let's see if we have a polar molecule of some sort. and we have an electron cloud with its negative charges, right? The same sort of thing can happen, right? We have a dipole that is going to pull on the electrons in that cloud. So the dipole will force the cloud to become polarized. Right? So again, we have an induced dipole. Right? So we will call this the Dipole-Induced Dipole. Okay, and in terms of strength, we're talking about something that's slightly less than dipole-dipole interactions. Right, now what's important about all of these, the ion dipole, the ion-induced dipole, the dipole-induced dipole, is that you have to have two things. Okay, so if I just ask the question, what forces are possible with CH4? There's no possibility of anything involving dipole-induced dipole, ion, anything, unless I said what are the forces involved if you have CH4 with sodium chloride. Okay, I have two things here. This one makes ions, this one does dispersion. Okay, then we have the possibility of one of these sort of hybrid forces. Right, so to talk about the ranking of all of this, right, so from weakest to strongest. Right, so our weakest is still dispersion. Right, the next strongest is the dipole-induced dipole. Right, and again, we have to have two things. We have to have a polar molecule and a nonpolar molecule. Next, we have ion-induced dipole. Right? Again, we need two things. We need an ion and we need a nonpolar molecule. Right? Next, we have our pure dipole-dipole. Then we have our hydrogen bonding. And then we have our ion dipole. And this is our strongest. Right, now we do have one more to talk about, and that's simple ionic forces. And technically they are the strongest of all. Right? But they're sort of separate because we're not talking about interactions between molecules, we're talking about interactions between atoms. Okay, so technically we could call ionic interactions, ionic forces, intramolecular, because we're not talking about interactions between molecules. And those are the interactions where we have a sodium plus interacting with a Cl minus, or a magnesium 2 plus with an oxygen 2 minus. Okay, these are the strongest forces there are. Right, so highest boiling points, melting points, things of that nature. Okay, they tend to be crystalline. Right, because they are so strong, they just form crystals, they go straight to solid. So yes, so I don't really count in ionic forces in this category, but they are the strongest. But they are technically intramolecular forces. Some textbooks don't even put them in the same section of the chapter. All right, so we're going to go ahead and stop this particular video, and we'll pick it up on the next video with phase diagrams.